My name is Kimia Forani. The name of this paper is Upper Limb Powered Exoskeleton Design, done by researchers from University of Washington. The reason I chose this paper is that I was interested in human skeleton-related studies and rehabilitation. An exoskeleton is an external structure mechanism with joints and links corresponding to those of the human body. Potential applications of the exoskeleton as a wearable robot include a therapeutic and diagnostic device for physiotherapy, an assistive device for human power amplification, a haptic device in virtual reality simulation, and a master device for teleoperation. To better understand kinematic and dynamic requirements of an exoskeleton arm for functional use, a pilot study was performed. Motions of the human arm were recorded during 19 activities of daily living using a motion capture system, and torques were calculated using modeling simulation softwares. Results of joint position and joint torque distribution about each axis are plotted to find positions of the arm that occur most commonly throughout daily activities. The mechanical human-machine interfaces are the physical components that mechanically couple the human arm and the exoskeleton structure and enable force transmission between them. To achieve axial rotation of exoskeleton limbs, three primary configurations are conceivable. The first two involve a single DOF bearing, while the third configuration involves an axis that is displaced from the anatomical axis and a minimum of two additional non-collinear axes. Exoskeleton is composed of three joint configurations: 90-degree joints, 180-degree joints, and axial joints. Together, the joints produce an exoskeleton structure that achieves full elbow and wrist functionality. Joint 1 and 7 are modeled as 180-degree joints, joints 2, 4, and 6 are 90-degree joints, and joints 3 and 5 are axial joints. Achieving mechanical joints that match those of the human arm is a challenging task, especially in cable-driven devices. In 90 degrees and 180 degrees configurations, the cable is wrapped around a pulley, which is concentric with the axis of revolution. Axial joints are represented by a series of 9 pulleys, each located at a constant radius from the axis of revolution, together acting as a single larger diameter joint pulley. I think slip rings could also be used for axial joints instead of using a series of 9 pulleys.